Hi, in this video, we're going to go through what are now continuous random variables and what are the similarities and differences between a continuous one and a discrete one. So, unlike discrete, which is defined over countable number of values, the continuous random variable is defined along the real line. So it's a subinterval or a subinterval of a real line. So it could be the whole real line or just an interval from maybe A to B, but it captures everything, all the real numbers in it. Some properties that it has is that the CDF of this continuous random variable is differentiable. That's one of the things that you also require for it to be a continuous random variable. So your CDF is differentiable, meaning your CDF will represent probability of x less than or equals to x is differentiable, and its derivative is known as the probability density function. So why is it called density? Well, density is like mass over volume or the mass over an area or some sort. So when you integrate this density, integrating is like finding the area, and so you integrate a density, you get back the probability. So basically that's how the naming works. So it's like unlike the one where we use for discrete random, where it's known as a PMF, probability mass function, where probability of x equals to 2, this equals to the probability. For density, you need to integrate over an area in order to get the probability. So you can see that the probability of A to B will be the following, and so it is F is equal to the CDF evaluated as B minus away the CDF evaluated A because of this formula over here. And so you can rewrite it still to become this integral, and you should understand that from the calculus videos that I've done or any calculus course you have taken. And so the probability that x equals to a single value now has no meaning, not equals to 0 actually, not no meaning. And that's because the integral of a to a of fx dx equals to 0. And so for continuous random variable, that's where it differs from a discrete random one. There is no single value that can have a probability greater than 0. And so the only probability larger than 0 are when you have an interval. So you can see this figure to better understand it. So you got the probability density function drawn out. You have a region from A to B. Then this region, when you integrate it, will give you the probability that x lies within A to B. And you can see that if x is just a single value, for example, probability x equals to A, it equals to 0 because there's no area over here. And so we like to take some things to see in better view of what's the differences between a continuous versus discrete. For discrete, your CDF is Px less than or equals to x, which is the same as actually the definition for continuous, but then discrete you have PMF, for continuous you have PDF. And so everything on the discrete side you take a summation, and for continuous you just take an integral. Basically that's the main difference. And so when you have an expectation, you sum x times px equals to x. For continuous random variable, now our expectation is just integrate over the whole support of x fx dx, and you can just apply egx accordingly, and also linearity still holds because the integral linearity holds over an integral as well. So it has the common properties, but you just need to change the formula basically. from discrete to continuous, which actually you shouldn't be daunted by integral, as it is sometimes easier to evaluate as compared to a summation. We shall take a look at some examples now to better understand the differences and how do you apply continuous random variables. So for example, continuous random variable could be modeling the amount of time that a computer functions before breaking down. And they give you in this probability density function. If you read online, this will be also known as an exponential distribution or negative exponential. And so the question now is what's the probability that it functions between 50 to 150? Well, you see that there is an unknown here. And so what we need to do is we need to find the unknown first. And that's basically applying the property of a probability density function where we integrate over negative infinity to infinity, it should be 1. So it's basically like summing up all the probabilities. So it has to equal 1. And because when it's less than 0 is 0, we just need to take from 0 to infinity, and it will be this integral lambda e minus 2 power minus x over 100. And we obtain, when we evaluate it, to be lambda equals to 1 over 100. And so when we want to calculate the probability now, you just need to integrate from 50 to 150 of this function, and you get the probability accordingly. Similarly, for functions for fewer than 100, you just integrate from 0 to 100 and you get the function, because the lower bound now is 0. I hope this is clear to you, and we shall move on. You can practice more in the textbook by Sheldon Ross, first course in probability. And so the next example, we will now prove more theoretical results. And one of the theoretical results that we can prove is that for a non-negative random variable continuous, the expectation is integral of 0 to infinity of the probability of y larger than y dy. And really, that's just saying that the CDF is this, and so the probability that y larger than y equals to the integral of y to infinity of fx dx. So basically fx now is the pdf, and we are just calculating what is this probability function over here. And so the integral of 0 to infinity of the following, you just need to exchange this term inside with the following integral function. And now what we want to do is we want to flip the order of the integral. And so how to flip it is using your techniques in multivariable calculus, which I'll make a separate video on. But for now, you can read online. But basically, if you have this line, you should know that when you have this is the y equals to x line. And so the first one is x running through y to infinity. So for particular y, for x from 0 to infinity, it's over here, is this portion. Then y runs from infinity. So now what, you got y over here. So you got y over here, I mean. For a particular x, you got y. Y runs to infinity. So it's everything is this portion is above the y equals to x line, basically. And so now we can flip it to say we want to integrate with respect to y first. And so we want a particular y. For a particular y, x runs from 0 to x. So you can see now, for this portion, for a particular y, x runs from 0 over here to x. And so the integral of the inside is 0 to x. And then the outside is now 0 to infinity. And really, when you do so, you get the integral of 0 to infinity of x fx dt. But since you know it's a non-negative random variable, then the following will result in it being ex, because now it's defined from 0 to infinity. So I hope the proof is quite clear, but you need to do some multivariable calculus. You can read more about it online, but basically this gives you another way to calculate the expectation of a non-negative random variable, which can come you useful in times. And so I'll end off this video because I won't want to rush it. I'll leave the distributions to another day for continuous. But basically, for discrete and continuous, you have almost the same properties, but just that the expectations, you can see their summations, now they are integrals. And so I won't go through the proof of why the ex is like this, or explain to you, because it's defined to be this integral, but it's a natural definition from how we have defined it from the discrete side. So that's all for this video. I'll catch you in the next one, where I'll go through what is a normal distribution and uniform. So see you around.